Hello, Math 201 students. We are looking at section 3.4, which is the derivative as a rate of change. This is going to be applying the fact that the derivative can give you the rate of change of a function, applying it to various circumstances. Physics would be a big application of this. So we went over in class example 1, but just in case this is used in next succeeding quarters beyond this, I'll look at this example again. If you already saw this in class, feel free to fast forward this part. But if we have the area of a circle as this function of its diameter, so we could say A of D equals pi over 4d squared, then how fast does the area change with respect to the diameter when the diameter is 10 meters? So when you're talking about finding how fast something is changing, you're talking about finding a derivative. So take the derivative of the area with respect to the diameter. So that means we do the power rule, bring the 2 down in front, so it becomes 2 pi over 4. Let me say A prime of D equals 2 pi over 4, which reduces to pi over 2 d, and then we subtract the exponent by 1, which makes it be d to the first. So if we want to know how fast that thing is changing with respect to diameter, we can plug any value we want to into the diameter to find how fast the area is changing when the diameter is that diameter. So now we're going to plug in 10, and we get 10 pi over 2, so A prime of 10 would be 10 pi over 2, which would be 5 pi when I reduce it. So the area is changing around a little over 15 meters per unit of time when the diameter is 10 meters. Let me correct myself there. It's not about 15 meters per unit of time. It's about 15 meters if you were to add, so when the diameter is 10 meters, if you then add another little bit of length to the diameter, then the area of the circle is going to change by about 15 square meters. This statement here actually gives a very thorough answer. When the diameter is 10 meters, the area is changing with respect to the diameter at the rate of 5 pi or 15.71 meters squared per meter. So if you add another meter to the diameter, the area is going to change by not just 1, but by 15.71 square meters. So that makes the units here work out the way that I was trying to think that they would, because the units here would be meters, but that's because it's meters squared per meter, and if you reduce that, that works out to be meters. All right, let's get on into physics when it comes to calculus. All right, suppose that an object is moving along a coordinate axis. So it means it's moving in a straight line. Usually we talk about that as a horizontal or a vertical direction, so that we know its position on that line is some function of time. So you have the position as a function of time, and you have some equation for that. The displacement of the object is the change in position. So it would be f of t plus delta t. That's like the second point of position, right? Minus f of t. So that's the first point of position, the change in position. Position 2 minus position 1. This is hopefully going to start looking like the limit definition of a derivative, where delta t is in place of the h. So average velocity is displacement over time. So it's position 2 minus position 1. That's the change in position, aka displacement, over the change in time. But what if we don't want to just find the average velocity? We want to find the velocity at the moment. What is the current instantaneous velocity? And so what do we do to do that? We can make this into instantaneous velocity instead of average velocity by doing what? How can we make it into a calculus issue? By taking a limit. The limit, as used to be, we used to say h, but in this case we're saying delta t. The limit as delta t approaches 0. So we're making the time interval become nothing so that it's at an instant instead of over an interval of time. Right, besides telling how fast an object is moving along a horizontal line, its velocity tells the direction of motion also. So velocity is a vector, meaning it needs two numbers to tell what it is, not just a size or a magnitude, but it also needs a direction. Velocity can be positive or negative depending on which direction you're going. When the object is moving forward, in other words, s, or the position, is increasing, the velocity is positive. When the object is moving backwards, then s, by the way, s here means position. It doesn't mean speed. S is a generic letter in physics that means the position axis. It could be an x-axis or a y-axis or a z-axis. So they use the letter S to represent just a general direction of an axis. So the position is decreasing when you're moving backward. And when that's the case, the velocity is negative. All right, if the coordinate line is vertical, the object moves up for positive and velocity moves down for negative velocity. The blue curves in figure 3.15 represent position along the line over time. So here's position. All right, so over time, this position right here is increasing. That means it's moving in the positive direction. It's getting farther from the object. It's getting farther from its origin in the positive direction. Here, over time, the position is decreasing. This means it's getting closer to its origin over time. The zero value here being whatever arbitrary point you want to call zero, or the origin. All right, however, the speed, all right, when we talk about speed, like on your speedometer doesn't say 30 miles per hour. It doesn't say negative 30 miles per hour when you're going backwards, or when you're going, when you're returning home from work. It doesn't say negative 30. It just says 30. Because speed is the absolute value of velocity. Speed is what's called a scalar. It only has a magnitude. It does not have a direction. It's not concerned with direction. All right, so let's look at this graph of velocity. And I just want us to be able to tell just kind of whether the velocity is telling us that the object is moving forward or moving backward, and whether the object is speeding up, remaining at a constant speed, or slowing down. All right, so we're looking at a graph not of position in this thing, but of velocity. We can tell that because it's got a V right here, velocity over time. So in this first time interval from 0 to 1, the object has a positive velocity. That means it's moving in the forward direction, and its velocity is increasing. So it's speeding up. The second, it's still moving forward with a constant velocity this time. So its position is still increasing during this time, because velocity is a positive value. So it's still moving forward. During the time interval from 2 to 3, the velocity is still positive. It's still a positive value for velocity. So the object is still moving forward. But what this means is that the object's velocity is decreasing. So it's slowing down even though it's still moving forward. All right. Finally, at time 3, the object has 0 velocity. So it is stopped for a small moment. And then it goes into a negative velocity. So it changes its direction. So if it's going a positive velocity and then 0 and then a negative velocity, that means at this moment right here, when it hits 0, it is changing its direction from forward to backward. So it's like, think of an object going up, going up and then reaching its apex and then changing its direction and then coming down. All right, so now the object is going down, and the velocity is negative, so the object is moving backward. It's moving in the negative direction. Its position, we could say its position is decreasing, or we might want to say its position is increasing in the negative direction. Either way you want to say that. And its velocity is, you could say, decreasing or increasing in the negative direction. So its speeding up backwards or speeding up, moving in the negative direction. Here, it reaches its maximum negative speed, or you could say its minimum speed, which is the same thing as a maximum negative speed here. All right, and now it's still moving backwards because its velocity is still negative, but its velocity is slowing down in the negative direction. That's kind of confusing because its velocity is increasing, but that's the same thing as saying slowing down in the negative direction. All right, until it gets to 5. At time 5, the object is not moving. It's got a velocity of 0. It's standing still, and it's going to stand still over this whole second right here until it gets to second number 6. Then there's a positive value for velocity, which means the object is moving in the forward direction again, or in the positive direction. And it's increasing, the velocity is increasing, so it's speeding up. It's going faster and faster in that positive direction. All right, so we've already talked about how velocity is the rate at which the position of an object changes. There's also what's called an acceleration, which is the rate at which an object's velocity changes. So the rate of change of position is velocity. The rate of change of velocity is acceleration. The acceleration measures how quickly the body picks up or loses speed. In Chapter 13, we will study motion in the plane and in space, where acceleration of an object may also lead to a change in direction. All right, so I want you to kind of feel what position and velocity and acceleration feel like physically. Position is just where you are. Okay, so if you're riding in the truck and you pass by McDonald's, your position is McDonald's. All right, your velocity is how fast you are changing that position, how fast you're moving. It's what your speedometer says. So if you're at McDonald's and you get all the way to I don't know, Dairy Queen, a mile down the road, and you get there in let's say 30 seconds, then you're going 1/30th of a mile per second. All right. So, and if you are not changing that velocity, if you're going that velocity the whole time, the same velocity, you won't even feel that motion. There will be no feeling of movement. You can look out the window and see things passing by to know you're moving. But if you were just asleep, or the car was blacked out and you couldn't see out of it, you would not be able to perceive that you are even moving, because going at a constant velocity requires no force. There's no force that is needed to maintain a constant velocity. So just like right now, you don't even know you're moving, but the Earth is moving, right? The Earth is rotating and the Earth is moving around the sun, and so, but it's doing it at a constant velocity, so that there's no external force having to be on you, so that you don't even feel the movement. Acceleration, however, is caused by a force, and that is something that you will feel. Acceleration, the feeling of acceleration is, let's say you're sitting at a red light, and let's say you're in a big hurry. So the right light turns green and you step on the gas and you feel the car seat pressing against your back. You feel yourself move, become almost one with the back of that car seat, because it's you're pressing against it and it's pressing against you. That force is what is the force that is causing you to accelerate. And so acceleration is something you can feel, not just see. All right, the acceleration is a change in velocity. All right, and then there's another concept that we don't talk about as much, but it's a sudden change. A change in acceleration is called a jerk. All right, when a car ride when a ride in a car or a bus is jerky, it is not that the accelerations involved are necessarily large, but that the changes in acceleration are abrupt. So think of jerk as step on the gas, step on the brake, step on the gas, step on the brake. Your head will move backwards when you step on the gas, and then be thrown forwards when you slam on the brake. All right, that's a large change in acceleration, and that's what is causing a jerk in your body. All right. So definitions. Acceleration is the derivative of velocity with respect to time. If the body's position at time t is f of t, then the body's acceleration at time t is, the acceleration is this. It's dv dt, in other words, the derivative of velocity, or d squared s over dt squared. In other words, the second derivative of position. The derivative of position is velocity. The second derivative of position is acceleration. Or you could say the derivative of velocity is acceleration. Okay, hope all that made sense. The jerk is the derivative of acceleration. So the derivative of position is velocity. The derivative of velocity is acceleration. The derivative of acceleration is jerk. So with all that said, you could say that the jerk is the third derivative of position, or it's the second derivative of velocity, or it's the first derivative of acceleration. Okay. Near the surface of the Earth, all bodies fall with the same constant acceleration. And it's the acceleration that's due to the constant force of gravity. And so since we have a constant force of gravity on Earth, near the surface, then we have a constant acceleration. And it is this little letter we call little g. That's the acceleration due to gravity. And little g in meters is negative 9.8 meters per second, or negative 9.8 meters per second squared. Now that's going to be the same acceleration for every object, whether it's a feather or a brick. The only reason a feather falls more slowly is because of air resistance. If there were no air, the feather and the brick would fall at the exact same rate. You should, if you want to see that in action, there's a really cool video on YouTube. You can search for it. Just search for this video right here. Watch a feather and a bowling ball fall at the same speed. I believe that's the right video. It's pretty cool to watch. All right. So the value of g, it could be, if it depends on the units we're using, it might be 32 feet per second, or 9.8 meters per second. And it's talking about how fast the velocity is changing. If it's 9.8 meters per second, that means it's changing by a rate of 9.8 meters per second every second. But when the way it works out is you say 9.8 meters per second squared. All right, the jerk, if it's a constant acceleration due to gravity, the jerk would be zero if we're talking about projectile motion or free fall motion. So if you jump off of something, you feel that gravitational acceleration, but it's not jerkiness. It's not like accelerating and then slamming on the brakes. That doesn't happen when you're in free fall. All right, so example 3. Figure 3.17 shows the free fall of a heavy ball being released from rest at time t equals 0 seconds. How many meters does the ball fall in the first 3 seconds? So we can see here, just using this little figure, in the first 3 seconds, every time you see this circle drawn, that represents 1 second passing. So you can tell that it fell 45 meters in the first 3 seconds. What is its velocity, speed, and acceleration when t equals 3? All right. Since we're dealing in meters, we're going to deal with this equation, the position s of t is equal to 1/2 gt squared, where g is negative 9.8. So s of t then is going to be negative 4.9 t squared. So then v of t is going to be the derivative of that. You take the 2, you move it down front, and then it becomes negative 9.8 t to the first. The acceleration is going to be the derivative of that. So the derivative of negative 9.8 t is what? It's just negative 9.8. So when t equals 3, to find the velocity, you just plug in 3. So v of 3 equals do it in my calculator here. Negative 29.4. Which means it's moving downward at that moment at a rate of negative 29.4. It's moving downward at a rate of 29.4 meters per second. That's fast. All right, the acceleration at that moment means you're going to plug in 3 to the acceleration. But notice the acceleration is a constant. There is not even a variable t that it depends on. No matter what you plug in, it's always a constant, negative 9.8. Which is kind of as we've said, gravity is a constant force. So we have answered that question. There's actually one thing we didn't answer. We answered velocity, we answered acceleration. What about the speed? Well, that's simple. It's just the absolute value of velocity. So the speed is just positive 29.4. Okay, here's a fourth example. A dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second, 109 miles per hour. It reaches a height of, here is our, what is this right here? This is what? This is the position function. All right, that's the position function. So if our position function, s of t, is 160t minus 16t squared, then the velocity, is going to be what? We can figure out velocity based on the position, because velocity is what compared to position? It is this is the good old Sunday school answer here. It is the derivative of position. So take the derivative of this, which would be 160 minus 32t. We may even want to do acceleration. What is acceleration? Acceleration would be the derivative of velocity, which in this case would be negative 32. So this equation is given in feet, by the way. Also, if you were to take a physics class, you would learn how this equation comes about. Like how does this equation in the very first place, how do we get that based on just the fact that it had an initial velocity of 160? All right, so now let's answer these questions. How high does the rock go? Okay, what can we do? What can we work with here to figure that out? So position, position is going to look something like that. Right, the rock's going over time, the height of the rock. We could say S or we could say Y or whatever. The height of the rock is going to reach some apex. All right, so one thing we could do is we could graph this and find the apex that way. But if we didn't want to do that, let's say we wanted to use some calculus to do this thing. What we could do, if we didn't have a calculator or something, we just wanted to use some calculus. That thing hits its apex when the slope is 0, or when the derivative is 0. Right? You throw something, it goes up, comes back down, but right at the very top, the velocity is 0 for an infinitesimally small moment, right? It's going up, so it has a positive velocity. Then it's going down, so it has a negative velocity. Well, if it's going to go from positive to negative, it's got to hit 0 at some moment. So again, we can do that two ways. We can graph this and find it in the graph, in the calculator, find the maximum. But I would want to prefer you to do, at this moment, to do the velocity equal to 0 and solve for t. So move the 32 over, 160 equals 32t, divide by 32, and t would equal t would equal 5 seconds. All right, that actually doesn't answer the question to part A. The question on part A asks, how high does the rock go? But what we just figured out was how long it would be before the rock reached that maximum height. So we found out the time when the rock gets to its highest point. Now, how can we actually figure out how high that highest point is now that we found the time? Well, we take that time and we plug it into that position function. And that will tell us what the position of the rock is at that moment. So the max would be S of 5, which would be 160 times 5 minus 16 times 5 squared. And if you type that in your calculator, I'm just going to go ahead and say that's 400. 400 what? 400 feet, because that's what our units are here. So we've answered part A. Then it says, what are the velocity and speed of the rock when it is 256 feet above the ground, on the way up, and on the way down? Good deal. So 256 feet above the ground, that's talking about what? That's talking about a position. It's 256 feet above the ground. That's a position. So 256 is the position. And if I want to know when that happens, then I'm going to solve for t. All right. I'll move my 256 over to the right. I'm going to go ahead and rearrange this equation. In fact, maybe what I want to do, instead of moving 256 to the right, I'm going to move these two terms to the left. That way my first term will be positive. I would rather my first term be positive. You could do it the other way too, but it's just kind of more comfortable for me, probably. Equals 0, and I'm going to factor. The first thing I could do is factor out a 16. That's t squared minus 5t plus 16. Sorry, I made a little mistake here. If I factor out a 16 from 160, it doesn't leave me with a 5, it leaves me with a 10. Okay, and now I believe this will factor more, so it's going to factor as t minus 8 and t minus 2. So divide both sides by 16. So the 16 goes away. And then set both of these equal to 0, and I get t equals 8, and I get t equals 2. So it reaches a height of 256 on the way up and on the way down. So on the way up, that would be after 2 seconds, and on the way down, that would be after 8 seconds. All right, that doesn't answer the question part B yet, but that will get me further to the answer. What does it want to know? It wants to know the velocity and the speed when this occurs. Well, now that I've got the time and I've got the velocity function right here, I can just do the velocity at those times, v of 2 and v of 8. So 160 minus 32 times 2, that's going to be 160 minus 64, which is going to be 96, I think. And then plug in 8, 160 minus 32 times 8. Let's see what 32 times 8 is. That's 160 minus 8 times 2 is 16. Carry a 1. 8 times 3 is 24. 25. 256. So what's that going to be? That's going to be negative 96. And we can kind of know that because when you throw that rock up, when it reaches whatever this height of 256, it's going to be going at the same speed up as it is on the way down, coming back down. That's the way it works with a parabola. It's symmetrical like that. So that answers that the velocity on the way up, when it's at that height, is positive 96, and on the way down it's negative 96, and the speed in both instances is just 96. Part C, what is the acceleration of the rock at any time t during its flight after the blast? Well, since we found the acceleration right here, and it's a constant negative 32, that's easy. The answer to part C is negative 32. That's the acceleration at any time t. All right, so that one was simple. Part C, when does the rock hit the ground again? Well, when the rock hits the ground, we're calling the ground a position of 0, a height of 0, so I set the position function equal to 0, and I solve for t. I believe first I can factor out a 16t as the GCF. That leaves me with 10 minus 16, no, 10 minus t. And then I set 16t equals 0, and I set 10 minus t equals 0. So for that one I get 0, which is obvious because it's on the ground when the problem starts. So when the clock starts at 0, it's on the ground. And I set this other one equal to 0, and I get t equals 10. So it hits the ground again. After it starts on the ground, it hits the ground once more after 10 seconds. So that's the answer to part D. That was a really good problem. That is a great just way to use calculus to do physics, doing derivatives and answering the questions using these equations of position, velocity, and acceleration. All right, next we're going to talk about not only derivatives in physics, but now derivatives in economics. Engineers use the terms velocity and acceleration to refer to the derivatives of functions describing motion. Economists, too, have a specialized vocabulary for rates of change and derivatives. They call them marginals. In a manufacturing operation, the cost of production, which we will do this function C of x as the cost of production, which is a function of x, which is the number of units produced. Units of whatever that company makes, widgets or whatever, golf balls or whatever it might be. The cost of production with x number of widgets being produced. The marginal cost of production is the rate of change of cost with respect to the level of production. So dc dx. All right. So that's going to be finding for us the rate of change of production with respect to just a small change in the number of units produced. How will that affect production cost if we produce a smaller or larger amount of units? All right, suppose that C of x represents the dollars needed to produce X tons of steel in 1 week. It costs more to produce X plus H tons of steel per week, and the cost difference divided by H is the average cost of producing each additional ton. So let's look at this. The cost of producing a little bit more of whatever this is, minus the cost of producing the original amount. So that's the difference in the cost divided by the difference in the amount of product. The difference in the cost divided by the difference in the amount of product. That gives us the average cost of each additional H units of product, in this case steel. But if you put a limit on it, then it's no longer an average cost. It is now a marginal cost. It is finding the instantaneous rate of change if you just change how much product you're producing by just a tad bit. Sometimes the marginal cost of production is loosely defined to be the extra cost of producing one additional unit, which is approximated by the value dc dx at x. This approximation is acceptable if the slope of the graph of c does not change quickly near x. Then the difference quotient will be close to its limit dc dx, which is the rise in the tangent line if delta x equals 1. The approximation works best for large values of x. Economists often represent a total cost function by a cubic polynomial. So you got this cubic, alpha x cubed plus beta x squared plus gamma x plus delta. So let's look at, just to get a picture. This is the cost of producing, marginal cost to produce one extra unit. And the slope of that tangent line, again, gives you the rate of change, or in other words, the marginal cost for producing one additional unit. All right, this cubic polynomial, and here's alpha, beta, gamma, delta as the coefficients of this cubic polynomial. Let's see what they represent, where delta represents fixed costs. So this constant right here is the fixed cost, such as rent, heat, equipment, capitalization, and management costs. The other terms represent variable costs, such as the cost of raw materials, taxes, and labor. So those kinds of things can change based on how many we produce. Fixed costs are independent of the number of units produced. You're going to pay that regardless of how many you produce. Whereas the variable costs depend on the quantity produced. The cubic polynomial is usually adequate to capture the cost behavior on a realistic quantity interval. So suppose that here we got this example 5. Suppose that it costs, this polynomial is giving us the cost of producing x units. And let's see what it says on the next page for this example. What's it going to ask us to do? To produce x radiators when 8 to 30 radiators are produced. And that R of x equals this, gives the dollar revenue from selling x radiators. Your shop currently produces 10 radiators a day. About how much extra will it cost to produce one more radiator per day? And what is your estimated increase in revenue for selling 11 radiators a day? All right, derivatives make this question really easy to answer. All right, I went ahead and wrote the cost function that was on the previous page. Take the derivative of that thing, c prime of x will be what? 3x squared minus 12x plus 15. Hopefully taking derivatives is second nature to you at this point. And we're trying to answer how much extra it will cost to produce one more radiator per day when we're producing 10 radiators. So now all we got to do is plug 10 into this marginal cost function, which is c prime of x. C prime of 10 is going to be 3 times 10 squared minus 12 times 10 plus 15, which is going to be 300 minus 120 plus 15. That's going to be 280 plus 15. That's 295. So it will, we would estimate that it will cost us $295 to produce one more unit. And then we want to answer this next part of this question. What is our estimated change in revenue? It says increase, but may not be an increase, maybe a decrease. But what's going to be the change in revenue for selling one more unit? Well, that would be found by doing the marginal revenue function, which is r prime, the derivative of revenue. That's going to be 3x squared minus 6x plus 12. And we're going to plug in 10 to that. R prime of 10 is going to be 3 times 10 squared minus 6 times 10 plus 12. So that's going to be 300 minus 60 plus 12. So that's going to be 300 minus 60. That's 240. 240 plus 12 is 252. I think I might have made a mistake back here on this. I think I did some bad subtracting. 300 minus 120 is not 280, it's 180. 180 plus 15 is 195. Sorry about that. You probably already knew that and caught my mistake, but anyway, at least I caught it now. So then maybe we could even make a conclusion now. We could make draw a conclusion about a decision. Because now if we're making 10 units, 10 radiators, if we per day or whatever, if we make one more, it's going to cost us about $195 in extra cost, but it's going to make us an extra $252 in revenue. Since what we bring in is going to be higher than what we have to spend, the decision is yes, we should make one more per day. We should go up to 11 per day. That's how decisions are made in business when you get mathematics involved and you make wise choices that way. Math helps us to optimize things. It helps us to optimize, to do business at an optimum level, to make the best, not just to do mediocre business, but to do the best business possible. Example 6. This is not going to be a happy example because it's about taxes, and we don't like them. To get some feel for the language of marginal rates, consider marginal tax rates. If your marginal income tax rate is 28% and your income increases by $1,000, so that means that marginal income tax rate is like how much your tax is going to go up whenever your income goes up. So if 28% is that marginal tax rate, then if you make an extra $1, then you're going to pay an extra 28 cents in taxes. If you make an extra $1,000, you're going to have to pay an extra 28% of that 1,000, which is going to be about an extra $280 in taxes. All right, and that's going to depend. You can read the rest of that problem yourself, but it depends on if you land in a higher tax bracket, then your marginal rate will be even higher than that. When a small change in x produces a large change in the value of a function f of x, we say that that function is relatively sensitive to changes in x. That's sensitivity to change. The derivative of f prime of x is a measure of this sensitivity. Our example 7 gives us an example where calculus applies to genetics. Genetic data and sensitivity to change. I'm loving how we can see in all these examples that how math is everywhere and how it can be so useful in just about every category of life. All right, so in this example, the Austrian monk Gregor Johann Mendel in the 1800s, working with garden peas and other plants, provided the first scientific explanation of hybridization. I would think hybridization would be something like crossing peas with each other or trying to change the way that a garden pea would come out, trying to improve it. His careful records show that if p, a number between 0 and 1, is the frequency of the gene for smooth skin in peas, which is dominant in this case. So in other words, you could also think of p not only as a frequency, but as a probability. So it's like the probability that the gene for smooth skin in a pea would appear in that pea, would have that, and that a pea would have that gene. And the complement of that, 1 minus p, is the frequency of the gene for wrinkled skin in peas. So that's the probability that a pea would have the gene for wrinkled skin. Then the proportion of smooth skin peas in the next generation will be, and he figured this out. I'm not exactly sure, don't know enough about it to say how he got that equation, but it probably did a lot of thinking. The graph of y versus p suggests that the value of y, let me see what y even stands for, the proportion of smooth skin peas in the next generation. So it's smooth skin peas to all other peas. So the higher y is, the higher number of smooth skin peas you have. And it's based on the frequency or probability of the gene in the p's, the different genes. So if you graph y versus p in this figure over here, it suggests that the value of y is more sensitive to a change in p when p is small than when p is large. All right, so here's the graph. Yeah, so that makes a lot of sense. If you were to change, it's very steep right here, but it's getting less steep over here. So if you change p by a little bit, in other words, if you introduce a few more smooth-skinned peas into that garden or whatever, just a few more at the very beginning, it's going to make a dramatic impact. It's going to go up by a lot because you're increasing that proportion in this. But if you got mostly, so like over here, a value of 1 here would mean that it would be all smooth skin. But over here, this almost would mean there would be almost no smooth skin peas. So if you got almost all smooth skin peas over here, introducing a few more is not going to change that proportion very much. And we can also see that same concept going on in the derivative, because if you're at 0 smooth skin peas, I should say, then the derivative has a relatively high value of 2, which means if you change it by a little bit there, it's going to change it by a lot up here, or by 2. But as you get closer to 1, as you get closer to that frequency being 1, so you're having almost all smooth skin peas, you can see that if you change it by a little bit, it's not going to be changing by much. In fact, once you get to all smooth skin peas, adding a couple more smooth skin peas is not going to change it at all, because the derivative has a value of 0 there. All right, I hope that wasn't too confusing. I'm going to read the rest of this. Maybe if it was confusing when I talked about it, maybe this will help clear it up. The graph of y versus p in the first figure suggests that the value of y is more sensitive to a change in p when p is small than when p is large. Indeed, this fact is borne out by the derivative graph in the second figure, which shows that dy dp is close to 2 when p is near 0, and close to 0 when p is near 1. The implication for genetics is this: introducing a few more smooth skin genes into a population where the frequency of wrinkled skin peas is large will have a more dramatic effect on later generations than will a similar increase when the population has a large proportion of smooth skin peas. Now maybe the skin of a pea isn't very appealing to you, but you can hopefully see just by this simple example that this kind of math can be powerful. Maybe we care a lot more about the gene of a cancer cell, or the gene of high intelligence, or the gene of genes for various things that we do care about in people, maybe, than we do about the smoothness of the skin of a pea. Although maybe it's kind of nice also to get better peas in our meals, or to get better milk, or to get better beef, or whatever it may be. Obviously this is helpful for farming. And what does farming do besides, just feed the world and determine the level of enjoyment we get from a meal and the amount that it costs us to eat? When you improve the genetics of things in farming, you can improve all those things. And math obviously can play a role in that, a big role. That's the last example in section 3.4. All right, so good luck on 3.4 homework. I did remove a couple of questions that I thought were a little tougher. So if you have any questions on these homework questions, you can ask me in class next time. See you next time.